Hello, this is a video presentation of a gait analysis framework for Parkinson's disease patients. Our goal is to secure accurate kinesiology imprints of Parkinson's disease patients through stereoscopic video capture and use that information to acquire raw 3D motion data with motion capture techniques in order to recreate an animated 3D skeleton representation of a patient's gait and calculate quantifying kinesiology metrics which represent the extent of gait abnormality. The information obtained is intended to provide physicians with essential quantified data by performing a gait analysis for every scheduled session in order to better assess the progression of the disease and thus improve the patient's treatment. Here is a demonstration of the 3D motion data acquisition through motion tracking of specified joints using video recordings from 2 camera views. As you can see, the results of motion tracking give us the necessary information to reproduce an animated 3D representation of human gait, which you can see in the 2 bottom windows of the presentation. What you can see here is the actual 3D motion tracking process. On the right, you can see a list of specified joints which are determined for both camera views. By selecting the desired joint and determining its location in both camera views for every frame of the recorded video capture, it is possible to calculate the 3D coordinates of a joint throughout the duration of gait. By doing this for every desired joint and for every frame of the recording, we are able to acquire 3D motion data which describes human gait and therefore reproduce an animated 3D representation or even use that information to calculate meaningful kinesiology metrics like the ones which we'll be presenting consequently. The 3D motion data obtained is used to calculate kinesiology metrics such as the thigh to shin angle during gait, which compared to that of a healthy individual can indicate the abnormality regarding the gait structure. This is how the thigh to shin angle structure looks like for a healthy individual, where the blue structure represents the left leg and the red structure represents the right leg. This is how the structure of the thigh to shin angle looks like for an early stage PD patient, whereas the structure of the thigh to shin angle of an advanced stage PD patient looks like this. These graphs show a comparison between a healthy individual and 6 early stage Parkinson's disease patients regarding the thigh to shin angle of a full gait cycle for the left and right leg respectively. By calculating the difference of a gait cycle between the left and right leg of a healthy individual and an early stage PD patient, we can observe the abnormality of each leg during gait. On the left, from top to bottom, you can see the difference between the left foot of early stage PD patients 1 to 6, which are represented with the red line, and the left foot of a healthy individual, which is represented by the green line. The result is the black line, patient minus healthy. In the middle, from top to bottom, you can see the same calculation as before, only this time for the right leg. Finally, on the right, from top to bottom, you can see the difference between the left leg, which is represented by the blue line, and the right leg, which is represented by the red line, of patients 1 to 6. The result, left leg minus right leg, is again the black line. By calculating and analyzing the logarithmic power spectrum of the thigh to shin angle, it is possible to determine whether the left or right side of a PD patient has a more pronounced problem. What you can see here is the discrete frequency spectrum of the log power thigh to shin angle signal previously calculated for early stage patients 1 to 6 regarding the left and right leg respectively. The x-axis shows the frequencies in Hertz, while the y-axis shows the logarithmic power amplitude. For patients P3 and P6, the power spectrum at higher than mid frequencies hangs lower for the left leg than for the right, which indicates that the contribution of the left leg is less than that of the right, and thus it has a more pronounced problem. The opposite is observed for the remaining patients, which indicate a more pronounced problem on the right leg. Apart from the thigh to shin angle, other essential kinesiology metrics can also be calculated, such as cadence, velocity or stride, and step length. Although the presented motion analysis framework is very accurate, it is also greatly time-consuming. Our future work is intended to focus on automating the motion analysis process and developing a patient-centric online medical information system which will provide physicians with a session-based historical record of essential kinesiology metrics and motion data. Before we close with this presentation, we would like you to bear in mind that the presented motion analysis framework, although originally developed for the gait analysis of Parkinson's disease patients, can also be applied in many other medical conditions to determine gait abnormalities, or can even be used in applications regarding different fields such as sports. In the medical field, it is important to understand that these studies provide critical data for the understanding and forging of the necessary knowledge to manufacture and test new drugs in order to optimize treatment. This was a video presentation of a gait analysis framework for Parkinson's disease patients. Thank you for your time.